in front of you is not a sphere. It is a mask. One side, smooth and dark and familiar, has been turned toward Earth for 4.5 billion years, locked there by tides older than oxygen. The other side is taller, paler, scarred in ways that should not be possible, and hiding something the textbook answer cannot explain. Tonight, we will follow 4 astronauts on a crewed flyby of the Moon, the first crewed flight beyond low Earth orbit since Apollo 17 in 1972. From a launch pad in Florida to the hidden hemisphere and back, and understand what that ancient, scarred face reveals about one of the deepest unsolved questions in all of planetary science. Before we dive in, if you love exploring deep space science as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. You have seen the Moon your entire life. Look at it long enough, and you begin to notice the same features arranged the same way. Those large, dark regions pooling across parts of its face, the pale highlands interrupting them, the bright spray of ejecta fanning outward from certain ancient craters. You have seen this face so many times that you probably no longer truly see it at all. It has become part of the background of existence, like the particular color of a wall in a room you grew up in. Familiar, unremarkable, stable in a way that almost nothing else in your experience can match. But that stability, that extraordinary, unbroken sameness, is not accidental. It is one of the most remarkable facts in all of planetary science, and most people walk beneath it every night without pausing to wonder why. It was there the night you were born. It was there 10,000 years ago, high above the first permanent human settlements, rising along the Tigris and the Euphrates. It was there 400 million years ago, when the first vertebrates crawled onto the land, larger and brighter in the sky, because the Moon was closer then, its presence heavier. It was there before there was an atmosphere on Earth at all, hanging in a sky above a world of boiling oceans and volcanic violence, always showing us, or what would eventually become us, the same patterned face. For 4.5 billion years, the same face, never any other. The textbook answer is that the Moon always shows us the same face because of a gravitational process called tidal locking. The Moon's rotation around its own axis has synchronized with its orbital period around Earth, so it completes one rotation for every one orbit, and as a result, the same hemisphere always faces us. This sounds, when you read it in an introductory textbook, like a neat and almost inevitable outcome. Tidy, clean, essentially unremarkable. A curiosity of celestial mechanics, the sort of thing worth mentioning once before moving on. The Moon is tidally locked. Yes, understood. Next topic. But here is what almost nobody tells you about tidal locking, and what the clean textbook summary leaves entirely out of the picture. The process that created this condition was not gentle. It was not gradual in the way we often imagine geological processes to be. And the fact that it happened the way it did, producing the specific face that has watched over all of Earth's biological history, was not inevitable at all. It was, in the deepest sense, an accident, and an extraordinarily consequential one. When the Moon first formed, approximately 4.5 billion years ago, from the debris of a colossal collision between the early Earth and a Mars-sized body that astronomers call Theia, the Moon was spinning freely. It rotated around its own axis at some rate independent of its orbit, the way planets and moons in the early solar system tended to spin, chaotically and individually, without constraint from their neighbors. If you had been observing the Moon from space in those earliest days, you would have seen every side of it in succession as it turned. The far side would have been visible. The near side would have been visible. They would have traded places in the sky continuously, like a slow sphere rolling in the dark. Then Earth's gravity began to work on it. The mechanism is subtle but relentless. Because the moon has some variation in its density and shape, Earth's gravity pulls more strongly on the slightly closer, slightly denser side at any given moment, creating a tiny but persistent torque. This torque creates a tidal bulge, a slight deformation of the moon's shape, as if Earth's grip were gently squeezing it. In the early moon, still largely molten, this bulge was not in rigid rock, but in liquid magma, and it sloshed slightly ahead of the moon's rotation, the way water in a turning bowl sloshes ahead of the spin. That sloshing created friction. That friction dissipated rotational energy, and the moon slowed. It slowed over hundreds of millions of years, decelerating steadily under the patient pressure of Earth's tidal grip, until at some point deep in the Hadean Eon, its rotation matched its orbital period exactly. One face locked permanently toward Earth, one face locked permanently away. The technical term is synchronous rotation, when any orbiting body's rotational period precisely equals its orbital period. But synchronous rotation, despite its clinical precision, represents something more profound than the mechanics alone suggest. It means that one entire hemisphere of the moon, approximately 19 million square kilometers of ancient stone, has been facing the cosmos in darkness, facing the stars, facing a universe that holds no Earth in its field of view, for nearly as long as complex chemistry has existed anywhere. It means the far side has been, in a sense, alone. And it means that for the entire span of human consciousness, every myth, every religion, every navigation system, every love poem ever written under the moon's light, humanity has been intimate with exactly one hemisphere of one celestial body. We have never, in all of our history, seen the other side directly. Not from the ground, not with any instrument built before 1959. The far side of the moon, a world roughly the size of Africa, was as unknown to us as the interior of a star. Picture yourself on a clear night, somewhere away from city light, lying on your back in grass or on stone, with the moon high overhead. The light from it is extraordinary in its quality, not white exactly, more silver-grey, with a softness that makes shadows seem almost physical. You have probably looked at this light your entire life and never thought of it as strange. You have probably never stopped to consider that every photon arriving at your eyes from that direction bounced off a surface that formed more than 4 billion years ago, that the very rocks producing that reflection were laid down before the first single-celled organisms existed on the body you are lying on. Look at the dark regions. In the upper portion of the face, toward the moon's north, a large dark plane covers much of what appears to be the moon's upper left. In the lower regions, further pools of darkness mark the great ancient lava basins, the Sea of Tranquility, the Sea of Serenity, the Sea of Rains. These dark plains are called Maria, from the Latin word for sea, a name given by early astronomers who believed, incorrectly but understandably, that these smooth, dark regions might be bodies of liquid water. They are, instead, vast sheets of solidified basaltic lava that flooded the moon's great impact basins somewhere between 3 and 4 billion years ago, filling them like ink poured into shallow depressions in stone. They are darker than the surrounding highlands, because basalt is darker than the ancient calcium-rich rock, called anorthosite, that makes up the pale lunar mountains. That contrast, dark plains against pale highlands, is the face we know. That is the face that has anchored human imagination for 100,000 years. The near side is dominated by the lunar mare, the vast, dark-colored remnants of ancient lava flows. The crater-pocked far side, on the other hand, is virtually devoid of large-scale mare features. Something profoundly different happened on one hemisphere compared to the other. For most of human history, that difference was not just unexplained, it was unknown. We had never seen the far side at all. That changed on October 7, 1959. On that date, a Soviet spacecraft called Lunar 3 completed a swing around the far side of the Moon and began transmitting photographs back to Earth. It was not a landing mission. It carried no instruments for chemical sampling or seismometry. Its scientific payload was essentially a pair of cameras, fixed focus lenses loaded with photographic film in a pressurized canister, and a radio transmitter to send the processed images across the 400,000 kilometers separating the Moon from the Soviet receiving stations spread across the territory of the USSR. The spacecraft's trajectory had been carefully planned to carry it around the far side, use the Moon's gravity to bend its path, and emerge on the other side with the cameras trained back at the hemisphere it had just passed over. This was a remarkable feat of engineering for 1959. Sergei Korolev, the brilliant and largely anonymous chief designer who had overseen the Soviet space program's early triumphs, Sputnik, Lunar 1, the first probe to reach the Moon's surface, had driven the development of Lunar 3 as part of an accelerating program of lunar exploration. The competition with the United States was fierce, the pressure immense, and the technical challenges of a far-side photography mission were genuinely daunting for an era when digital imaging did not exist, when computers occupied entire rooms and calculated trajectories with far less precision than a modern smartphone, and when the only way to return photographic data from a spacecraft was to develop the film on board and transmit a scanned television image of the developed negative across the void. The images that arrived at the Soviet receiving stations were grainy, blurred, swimming in noise. About 40 frames were usable at all. By the standards of what the Lunar Reconnaissance Orbiter would deliver 50 years later, they were barely photographs at all. And yet, the scientists analyzing them could see, even through the grain and the artifact and the distortion, that the far side of the Moon was different, profoundly, structurally different. In 1959, the USSR's Lunar 3 spacecraft flew around the Moon and sent pictures of the far side back to Earth. Though the images were grainy and black and white, they were still revealing. They showed that the far side was different. It has more craters and fewer of the dark volcanic plains called Maria that characterize the near side. The contrast between the two sides immediately raised questions about how the Moon formed and evolved. Scientists wondered if Earth's gravitational influence was responsible, or if the thickness of the crust was different. That is the remarkable thing about the initial reaction to Lunar 3's images. Scientists did not simply note that the two sides looked different and moved on. They immediately recognized that the difference required an explanation, that it was the symptom of some deeper asymmetry in the Moon's formation or evolution, and they could not, in 1959, provide one. The puzzle was handed down from generation to generation of planetary scientists, studied, probed, returned to, reformulated, and never definitively resolved. For 66 years, it waited. Now stop here for a moment, because there is something worth dwelling on before the story moves forward. The Moon is not a distant or exotic object. It is, by astronomical standards, essentially attached to us, a companion body so close that humans can see craters on it with the naked eye, so close that light takes barely more than a second to cross the distance between us. We have been studying it with optical instruments since Galileo turned his telescope toward it in 1610. We have sent robotic orbiters, landers, rovers, and sample return missions to its surface. 12 human beings walked on it between 1969 and 1972. And yet, the most fundamental question about its geology, why its two faces are so different, remained unanswered into the third decade of the 21st century. That fact alone tells you something about the depth of the mystery. Some scientific problems are hard because we lack data. Some are hard because the data is ambiguous. Some are hard because every new piece of evidence points in a slightly different direction, and the picture grows more complicated the more carefully you look. The lunar dichotomy belongs in that last category. The more precisely scientists have measured the moon's structure, composition, and geological history, the more clearly they have seen that the difference between the near side and the far side runs deeper than any single explanation comfortably accommodates. The near side is different, not just at the surface, but all the way through. Its crust is thinner. Its mantle has a different composition. It contains a concentrated abundance of specific radioactive and rare elements: potassium, rare earth elements, and phosphorus that exist nowhere else on the moon in comparable quantities. These elements, collectively called creep by geochemists, are geologically interesting because they produce radioactive heat, and heat drives volcanism. The creep terrain, the technical name for this compositionally distinct region on the near side, is one of the key reasons the near side experienced so much more volcanic flooding than the far side. But why is all the creep on the near side? Why is the crust thinner on the near side? Why did the volcanism concentrate there and not on the opposite hemisphere? These are not independent questions. They are different phrasings of the same question, which is, what happened to the moon and when to produce this extraordinary asymmetry? Why the two sides are so different is one of the moon's most enduring mysteries. It is a mystery with implications that extend far beyond lunar science. Because the moon formed from the debris of the same collision that shaped the early Earth, understanding the moon's asymmetry is inseparable from understanding the early Earth's interior. The minerals and elements concentrated on the moon's near side were, according to some theories, originally part of the Earth's mantle, delivered to the moon by the impact, and then sorted by forces we are still working to understand. If we can understand what happened to those elements on the moon, we gain a window into conditions inside the early Earth. Conditions that have been erased by billions of years of plate tectonics and volcanic recycling on our own planet. Scientists think Earth and the Moon have a shared origin, formed when a Mars-sized object collided with the proto-Earth about 4.5 billion years ago. While active geological processes have erased hints of our planet's makeup in those early years, the material from early Earth that formed the Moon remains largely preserved on our airless cosmic neighbor. The Moon, in this sense, is an archive, a frozen record of conditions that existed before the Earth we know had taken its current form. And the far side of the Moon, geologically quieter, less altered by the volcanic activity and impact-driven redistribution of material that changed the near side, is the most pristine portion of that archive. This is especially true for the lunar far side, where large regions have not been volcanically altered. Studying rocks here can give us insight into the early Earth while teaching us about the Moon's history. That archive had never been visited by human beings, not in all the time that human beings have existed. Take stock of where we are. The Moon has shown us one face for 4 billion years. The other face, first glimpsed in grainy Soviet photographs in 1959, turned out to be a geologically different world. Thicker crust, fewer volcanic plains, a landscape dominated by ancient impact scars rather than flooded lava seas. That difference points to a deep and unresolved mystery about how the moon formed, how it evolved, and what it can tell us about the early history of Earth. And for all the robotic missions that have mapped, orbited, and sampled the moon in the decades since Luna 3, the most fundamental question about the far side's nature remained contested, debated, and open. Then, on April 1st, 2026, 4 human beings strapped themselves into a spacecraft on the coast of Florida and began the journey that would carry them closer to an answer than any human had ever been. The story of the lunar dichotomy did not stop with Luna 3's grainy photographs. Over the 67 years that followed, a succession of robotic explorers peeled back layer after layer of the mystery, each mission revealing more than the last. And what they found, cumulatively, was a puzzle that grew stranger the more carefully it was examined, a problem that seemed to clarify with every new dataset, only to deepen once again when the implications were fully worked through. The first major structural revelation came not from optical imaging, but from gravity. In September 2011, NASA launched 2 small spacecraft, identical twins informally named Ebb and Flow, into polar orbit around the Moon on a mission called GRAIL, which stood for Gravity Recovery and Interior Laboratory. The project was led by planetary scientist Maria Zuber of the Massachusetts Institute of Technology, one of the foremost figures in planetary geophysics, and its goal was to measure the Moon's gravitational field with a precision that no previous mission had achieved. The 2 spacecraft flew in precise formation, tracking the tiny changes in distance between them as they swept over regions of varying density and mass. Where the crust was thick, gravity pulled fractionally stronger. Where it was thin, fractionally weaker. By mapping these variations continuously over more than a year of orbital observations, GRAIL produced the most detailed gravity map of any planetary body beyond Earth. The results confirmed what geologists had long suspected, but could not precisely measure. The twin NASA GRAIL orbiters, launched in 2011, revealed that the far side's crust is about 20 kilometers thicker on average than the near side. To put that in physical terms, a crustal thickness of 30 to 40 kilometers on the near side lowlands and 50 to 60 kilometers on the far side highlands. This is not a minor variation. It is a structural difference so fundamental that it changes how the 2 hemispheres respond to impacts, how efficiently they retain heat from their interiors, and how easily any magma rising from the deep lunar mantle can force its way to the surface. For the first time, the dichotomy had a number attached to it. Not just a visual impression, more craters here, more dark plains there, but a hard architectural fact embedded all the way through the Moon's crust. 20 extra kilometers of rock pressing down on the far side. 20 kilometers separating the geological histories of the 2 hemispheres. The creep terrain deepened the mystery further. Geochemists studying the Apollo samples had long known that certain regions of the near side were anomalously enriched in a specific suite of elements. These elements are collectively known by the acronym CREEP, a large region on the Moon's near side with abundant potassium, K, rare earth elements, REE, and phosphorus, P. This collection of elements matters because several of them are radioactive: uranium, thorium, potassium-40, and radioactive elements produce heat through their decay. Where creep concentrations are high, the underlying mantle stays warm longer, remains partially molten longer, and generates the upwellings of magma that produce volcanic flooding of the surface. The creep terrain is, in a very real sense, the furnace that powered the near side's volcanic history, and it is almost entirely absent from the far side, not somewhat depleted, not partially reduced. Remote sensing observations have shown that the far side of the Moon has different geology and rock composition from those of the near side, including the abundances of potassium, rare earth elements, and phosphorus. The heat-producing elements that reshaped the near side are geographically locked to one hemisphere, concentrated in a region called the Procellarum creep terrain that corresponds almost precisely to where the lunar maria are most abundant. The far side has virtually none of it, and no one has been able to say with certainty why. The textbook version of events, the version you might find in a first-year geology course, says that the near side's thinner crust allowed magma to rise more easily, explaining why it has more volcanic plains. The logic seems straightforward. A thinner rocky lid means any melt working upward from the interior has less material to push through before reaching the surface. This makes intuitive sense, and for many years it was treated as the primary explanation for the dichotomy's most visible feature. But here is what that simple picture does not account for. The far side South Pole-Aitken Basin, the largest, deepest confirmed impact structure on the Moon, refutes that argument. The asteroid or cometary impact that created the 2,500-kilometer-wide SPA carved deep into the lunar crust and even excavated some of the mantle. Later impacts on top of the basin carved further into the crust, making it very thin. By the thin crust logic, the SPA should be the most volcanically active region on the entire Moon. Magma should have poured through that thinned floor for billions of years, flooding the basin with dark lava plains. Instead, only about 3 to 4% of the basin floor is covered in typical lava plains. Crustal thickness alone cannot explain the contrast in volcanic activity between the Moon's two hemispheres. Something else was needed. Something about what the rock is made of, not merely how thick it is. 3 major theories attempt to fill that gap, and each illuminates a different dimension of the problem. The first involves the thermal influence of the early Earth. When the Moon coalesced as a molten body from leftover debris of the collision between Earth and the Mars-sized object, it was about 15 times closer to us than it is today. It became tidally locked very soon after, when the Earth was still extremely hot from the force of the collision. In one model, the Moon's near side constantly faced an extremely hot post-impact Earth, with surface temperatures estimated to have reached around 2,500 degrees Celsius, and thus remained molten for longer than the far side. In this model, proposed and refined by researchers studying the Moon's earliest thermal history, since the accreting Moon rapidly achieved synchronous rotation, a surface and atmospheric thermal gradient was imposed by the proximity of the hot, post-giant impact Earth. This gradient guided condensation of atmospheric and accreting material, preferentially depositing crust-forming refractories on the cooler far side, resulting in a primordial bulk chemical inhomogeneity that seeded the crustal asymmetry. The thermal gradient created by Earthshine produced the chemical gradient responsible for the crust thickness dichotomy. The second theory is stranger and in some ways more beautiful. It proposes that the Moon was once not alone in its orbit. A nifty paper by Utsi and Asfaug suggested that maybe when the Moon formed, it had a companion moon that formed exactly opposite it in the same orbit. This companion moon's orbit would not have been stable, but it might have been just properly placed to make a very soft collision as they both orbited the Earth. This would have plastered the companion moon against the side of the Moon, giving it a thicker crust there. Then tides would have reoriented the Moon, so that face would be the far side. 2 worlds, circling Earth together in the ancient solar system until gravity finally brought them together in the softest possible collision. Not a shattering impact, but a slow merging, one absorbed by the other, the added mass compressing and thickening the receiving hemisphere until it became the far side we observe today. The third theory, developed by Menghua Zhu at the Space Science Institute of Macau University of Science and Technology and published in the Journal of Geophysical Research. Planets in 2019 proposes a giant impact not on the far side, but on the near side. Signs of such an impact should be visible in the structure of the lunar crust today, said Dr. Zhu. The scientists ran 360 computer simulations of giant impacts with the Moon to find out whether such an event millions of years ago could reproduce the crust of today's Moon as detected by GRAIL. They reported that the best fit in their simulations for today's asymmetrical Moon was a large body, about 780 kilometers in diameter, striking the near side of the Moon at around 14,000 miles per hour. Under this scenario, the impact would have thrown up vast amounts of material that would fall back on the Moon's surface, burying the primordial crust on the far side in 3 to 6 miles of debris. That is the added layer of crust detected on the far side by GRAIL. None of these three theories is definitively proven. Some researchers favor the thermal gradient model for its physical elegance. Others favor Zhu's giant impact model for its explanatory power over the creep distribution. Although several scenarios have been proposed to explain these asymmetries, their origin remains debated. This is not a failure of science. It is science doing precisely what science does when confronted with a genuinely difficult problem, generating multiple plausible hypotheses, testing each against available data, and advancing, slowly, carefully, toward a consensus that has not yet arrived. It does not explain with certainty how the creep terrain formed exclusively on the near side. It does not explain with finality why the far side's crust is thicker by a precise and consistent margin. It does not explain the deepest puzzle of all, why two hemispheres of a single body, formed from the same catastrophic event, experienced such fundamentally different geological histories for 4.5 billion years. These were the open questions on April 1st, 2026, when 4 astronauts climbed into a spacecraft named Integrity and prepared to become the first humans in more than half a century to travel beyond low Earth orbit. But before the mission itself can be understood, there is one more layer of context needed. The two most recent chapters in this long scientific story. The revelation of the SPA Basin's extraordinary scale and the first physical samples ever returned from the far side of the Moon. Pause here for a moment. We have been building a scientific foundation across 2 long sections of this story, moving carefully through orbital mechanics, geophysics, geochemistry, and planetary modeling. All of it serves a single purpose: to make what Artemis II witnessed above the far hemisphere genuinely comprehensible. Without this foundation, the mission is merely a dramatic flight around the Moon. With it, each photograph, each observation, each reported color nuance becomes a thread in a 4 billion year argument. That argument begins in the most violent event in the Moon's history. The South Pole-Aitken Basin is not an ordinary feature. It is not a crater in the sense that most people imagine craters. A circular scar, a bowl-shaped depression, the kind of thing you can see clearly in photographs of the lunar near side. The SPA is so large that its curvature follows the curvature of the Moon itself. You cannot stand on its rim and see across it. Its far wall is below the horizon. Its floor, stretching nearly 4 kilometers below the surrounding terrain in its deepest regions, is itself an ancient, multi-layered landscape pocked with later impacts, including some that are enormous by ordinary standards. The South Pole-Aitken Basin is the largest, deepest, and oldest impact basin on the Moon. It sits primarily on the southern far hemisphere, centered at approximately 56 degrees south latitude, and it spans an area roughly equivalent to the continental United States. The SPA Basin is thought to have been formed 4.2 to 4.3 billion years ago in the pre-Nectarian period, before the period of heavy bombardment that left its mark across the entire inner solar system, before even the formation of the Moon's own mare basins. It is among the oldest large-scale geological structures we can directly study anywhere in the solar system, and because the Moon has no plate tectonics, no weathering, no large-scale geological recycling, it has survived almost entirely intact. The same impact structure that was created 4.3 billion years ago is still there, still measurable, still preserving evidence of the conditions that existed when the solar system was in its infancy. The 2,500-kilometer wide SPA Basin is one of the largest and oldest craters in the solar system. The object that created it was not an asteroid in the conventional sense. It was something larger, a body possibly several hundred kilometers in diameter, traveling at a velocity that converted its kinetic energy into heat so intense that the rock it struck did not merely crack or shatter, but vaporized, melted, and splashed outward in waves of liquid stone that solidified as they traveled. The impact plunged through the lunar crust and into the mantle below, excavating material that had never before been exposed at the surface. In 2022, a team of researchers at Brown University, publishing in the journal Science Advances, proposed that the SPA's legacy extended far beyond the basin itself. The impact that formed the Moon's giant South Pole-Aitken Basin would have created a massive plume of heat that propagated through the lunar interior. That plume would have carried certain materials, a suite of rare earth and heat-producing elements, to the Moon's near side. If this model is correct, the SPA impact was not only the defining event of the far side's history, it was also, paradoxically, the engine that created the near side's geological richness. The creep material would have ridden the wave of heat emanating from the SPA impact zone like a surfer. As the heat plume spread beneath the Moon's crust, that material was eventually delivered en masse to the near side. If this hypothesis holds, the far side's deepest wound may have been the engine that gave the near side its most beautiful feature. According to this scenario, catastrophe on one face shaped the geology on the other. The far side's deepest wound is the near side's most beautiful feature. Catastrophe on one face created geology on the other. They are bound together, these two hemispheres, not by similarity but by consequence. An impact that size does not just scar a surface. An impact that size reshapes everything below it. An impact of that size may have rewritten the geological destiny of an entire world. Whether the Brown University heat plume model is ultimately confirmed or superseded, the scale of the SPA demands attention on its own terms. In the photographs captured by the Artemis II crew on April 6, 2026, as their spacecraft swept around the far hemisphere at 4,067 miles above the surface, the southern reaches of the far side included terrain shaped by SPA's aftermath. The ancient, battered highlands, the pale anorthosite, the absence of the dark volcanic plains that would have marked creep's presence. Every feature they photographed was, in some sense, a consequence of that ancient impact, either directly, in the thinned and exposed crust of the basin floor, or indirectly in the unaltered highland terrain that the SPA's opposite hemisphere had left behind. And before human eyes returned to the far side in April 2026, the most recent chapter of the SPA's story had been written by a Chinese spacecraft that landed gently on its floor and came home carrying 2 kilograms of the most scientifically valuable rock on the Moon. The Chang'e 6 mission launched from Wenchang Space Launch Site on Hainan Island on May 3, 2024. It was, from an engineering standpoint, a mission of formidable complexity. Not because reaching the Moon is straightforward, it is not, but because landing on the far side of the Moon requires solving a problem that landing on the near side does not. The far side has no line of sight communication with Earth. Signals from a lander on the far hemisphere cannot reach Earth directly. The Moon is in the way. To communicate with a spacecraft on the far surface, you need a relay satellite in a special orbit that can see both the lander and Earth simultaneously. China solved this problem with a mission called Queqiao-2, a relay satellite placed in a lunar orbit specifically designed to maintain communication between Earth and the far side surface. Without Queqiao-2, Chang'e 6 could not have landed on the far side at all. With it, on June 1st, the lander touched down on the lunar surface at Apollo Basin, an impact crater within the larger South Pole-Aitken basin. Apollo Basin, the landing site, is itself a remarkable geological location. At 490 kilometers across, it is one of the largest impact structures within the SPA. Its floor sits deep below the surrounding terrain. Material on its surface includes a mixture of ancient SPA ejecta, later impact debris, and some volcanic basalt that flowed through the thinned crust billions of years ago. It was chosen for precisely this geological complexity, the chance to sample not just one unit, but a mosaic of far-side history. The lander's robotic scoop and drill took samples with a total mass of 1,935.3 grams from the lunar surface. The machinery transferred these samples to a small ascent vehicle, which lifted off from the far side surface on June 3rd and rendezvoused with the waiting orbiter. The samples were sealed, the orbiter departed the Moon's gravity, and on June 25th, 2024, the capsule containing about 2 kilograms of samples landed by parachute at the pre-designated landing area of Siziwang Bana in Inner Mongolia. Search teams reached it within minutes. The analysis, led by Chunlai Li and colleagues at the National Astronomical Observatories of the Chinese Academy of Sciences, and published in National Science Review in autumn 2024, revealed how profoundly different the far side material was. The 1,935.3 grams of Chang'e 6 lunar samples exhibit distinct characteristics compared with previous lunar samples. This study analyzed the physical, mineralogical, petrographic, and geochemical properties of the Chang'e 6 scooped samples. The differences were immediate and sensory, even before the chemical analysis was complete. According to Hu Hao, chief designer of the Chang'e 6 mission, the returned samples appeared slightly more viscous and somewhat clumpier than the relatively fine, loose material collected by Chang'e 5. This tactile difference, the way the far side regolith held together compared with the fine, powdery near-side soil, reflects real compositional differences. More feldspar content, finer, more irregular particles, a surface more intensely weathered by 4 billion years of solar wind exposure in a terrain that had never been refreshed by volcanic flows. The chemical findings were equally distinct. In a separate study published in the journal Science in 2024, Cui et al. Dated fragments of volcanic basalt from within the sample and determined that the volcanic basalt fragments formed 2.83 billion years ago. The basalt contains a low abundance of elements that produce radioactive heat, which is insufficient to explain the eruption. The authors suggest that the thin crust below the impact basin allowed volcanism to persist in that region. This is an elegant and important finding. Volcanism did happen on the far side, in the Apollo Basin, 2.83 billion years ago. But it was not driven by creep heat. It was driven by the locally thin crust, the mechanical advantage created by the deep SPA impact, in the absence of the radioactive elements that powered the near side's volcanic history. The exception proves the rule. Where creep is absent, but the crust is very thin, limited volcanism can occur. Where creep is present and the crust is thin, extensive and prolonged volcanism occurs. The near side had both advantages. Most of the far side had neither. The water story told by the samples added yet another dimension. Analysis of the basaltic rock brought back from the SPA basin by Chang'e 6 yields a mantle source water content of between just 1 and 1.5 micrograms per gram of sample. This is extraordinarily dry. Among the questions the samples needed to answer was whether their water content was compatible with the giant impact theory of the Moon's formation. Modeling of the giant impact scenario suggests the mantle on the far side of the Moon should have less water than the near side does. The Chang'e 6 data fits this prediction, adding another layer to the portrait of a far side that differs from the near side not only in structure and chemistry, but in the very volatile content of its deep interior. They were drier than near side equivalents. They were depleted in the heat-producing elements. They were, in the most literal geological sense, more primitive, closer in composition to the Moon's original, unmodified mantle than anything previously brought back from the near side. The far side had not been refined by volcanic activity. It had not been flooded, resurfaced, or redistributed. It had simply waited, cooling gradually over 4 billion years, preserving a record that the more volcanically active near side had long since destroyed. Yet what the Chang'e 6 samples could not provide was what no robotic mission has ever been able to provide: context. A robotic scoop returns material from a single point without the ability to scan the horizon, to note the way one crater's rim differs in texture from another, to perceive color gradients that suggest different mineralogy, to apply the kind of interpretive geological judgment that trained human observers bring to a landscape. Robots return samples without observation. Human geologist astronauts return something harder to quantify, but no less essential: the integrated, in-context judgment of minds that have spent years learning to read stone. That is what 4 astronauts aboard a spacecraft called Integrity were positioned to provide, rising from a launch pad in Florida as the evening light faded over the Atlantic coast. Picture yourself somewhere along the Atlantic coast of Florida as evening settles over the flat scrubland and the marshes on April 1st, 2026. Miles away across the saw palmetto and cabbage palms, rising above the tree line against a sky that has gone from blue to amber to the deep rose of a Florida dusk, Launch Complex 39B stands illuminated by floodlights, so intense they make the structure glow white against the darkening horizon. On the pad, held upright by the metal arms of the launch tower, the Space Launch System rocket carries at its crown the Orion spacecraft that will carry 4 human beings to the vicinity of the Moon and back. The rocket is taller than a 30-story building. In the hours before launch, the vehicle is alive with sound: the hiss of liquid oxygen venting into the air, the groans of thermal contraction, the radio calls of hundreds of engineers monitoring thousands of systems across a vehicle whose complexity is almost beyond comprehension. Inside the Orion capsule, the 4 crew members of Artemis II are lying on their backs in launch positions, suited, helmeted, waiting. Reed Wiseman, Commander, a Navy test pilot who had spent 165 days aboard the International Space Station in 2014. Victor Glover, pilot, another naval aviator who had flown to the ISS in 2020 aboard a SpaceX Crew Dragon and served as pilot on a 6-month expedition. Christina Koch, mission specialist, who had spent 328 consecutive days aboard the International Space Station between 2019 and 2020, the longest single spaceflight by any woman in history, and who possessed a depth of experience with the psychological and physiological demands of long-duration spaceflight that no amount of ground simulation can replicate. And Jeremy Hansen, mission specialist, representing the Canadian Space Agency, a fighter pilot and astronaut who had waited nearly 17 years since his selection for this moment. Together, they had named their spacecraft Integrity. At 6:35 p.m. Eastern Daylight Time, ignition. The Space Launch System rose from the pad on a column of fire that produced 8.8 million pounds of thrust, the most powerful rocket ever to carry humans, lifting Orion and its 4 passengers into the dimming Florida sky. The moment of ignition is not quite what you might expect from a distance. There is light first, a bloom of orange and white expanding from the base of the rocket, so bright that it washes out everything around it. Then the sound arrives, not as a crack or a bang, but as a sustained physical pressure, a rolling concussion that you feel in your chest and your stomach before you hear it with your ears. The rocket climbs, slowly at first, impossibly slowly for something so bright and so violent, and then faster, and then it is shrinking against the sky, and the sound is still arriving, still rolling outward across the flat Florida landscape. And by the time the sound fades, the spacecraft is already a white dot in the darkening blue. Artemis II was a crewed flyby of the moon. It was the first crewed flight of the NASA-led Artemis program, and the first crewed flight beyond low Earth orbit since Apollo 17 in 1972. That gap deserves to be acknowledged before the story moves forward, because it is not simply a number. 53 years, 4 months, and some days. That is the interval between the last human being to travel beyond Earth orbit and the 4 who began that journey again on April 1st, 2026. A gap so long that the youngest person alive when Apollo 17 left Earth in December 1972 was in 2026 in their mid-50s. A gap that contained the entire careers of most of the engineers who designed and built the SLS and Orion. A gap across which the institutional knowledge of how to do this, how to truly prepare human beings for the conditions beyond low Earth orbit, had to be rebuilt almost from scratch. They had trained for this for 3 years, the 4 of them together, learning the spacecraft, memorizing the mission profile, studying the geology of the lunar surface until they could identify craters and basins and structural features from orbital imagery the way a naturalist identifies birds in flight. They had practiced every system failure, every emergency procedure, every scenario the mission designers could imagine. They had spent hours in simulations of the communications blackout that would isolate them from Earth for approximately 40 minutes as they passed behind the moon. They had rehearsed the lunar science observation period until the protocols were automatic. Artemis II was the second flight of the Space Launch System and the first crewed flight of the Orion spacecraft, named Integrity by the 4-person crew. The name they chose is worth pausing on. Not Discovery, not Endeavour, not the kind of name that gestures toward exploration or ambition. Integrity, a word that implies wholeness, structural soundness, the quality of holding together under pressure. It is the kind of name engineers use to describe a system that does what it is supposed to do, that does not fail when it is tested. And it carries, perhaps, a secondary meaning as well. The integrity of the scientific mission, the commitment to honest observation and honest reporting of what those 4 human eyes would see above the far hemisphere. During the first day in space, the astronauts and teams on the ground checked out the spacecraft, named Integrity by the crew, to confirm all systems were healthy ahead of the transit to the moon. This was not a formality. The memory of Artemis 1 was present in every system check. The uncrewed Artemis 1 test flight of 2022 had revealed an unexpected heat shield erosion issue during re-entry, material ablating in ways the models had not predicted, at higher rates and in more distributed patterns than expected. Engineers had spent months analyzing the problem, determining its cause and devising a solution. For Artemis 2, rather than replacing the heat shield entirely, NASA modified the re-entry trajectory, a steeper direct entry to reduce the duration of the highest thermal stress. This change would limit further char loss while remaining within Orion's structural and thermal margins. The change worked. The Artemis 1 problem would not recur. But in those first hours of the mission, none of that was yet known. What was known was that the spacecraft was healthy, the crew was healthy, and 4 human beings were in orbit around Earth for the first time, with the specific intention of leaving that orbit and traveling to the moon. Among those 4, Victor Glover occupied a specific historical position that no press release could fully communicate. When Orion completed its translunar injection burn and Glover crossed beyond low Earth orbit, he became the first black astronaut in history to travel beyond low Earth orbit and around the moon. Jeremy Hansen, his crewmate, became the first Canadian ever to travel beyond Earth orbit. These facts sit alongside the mission's technical objectives, not as footnotes, but as something more essential. Evidence that the world which was not watching when Apollo launched now was, and that the people who represented that world in the Orion capsule were not symbols, but trained, skilled, determined professionals who had earned every moment of what came next. It is worth staying with that for a moment. The moon has been observed across the full span of human history by people of every culture, every language, every civilization that has ever existed on Earth. Its light has fallen on every human face that has ever existed. And in the entire 57-year history of human spaceflight, it had been visited, even just orbited or flown past, exclusively by American and Soviet men, a narrow demographic corridor by any measure. Artemis 2 did not fix that narrowness entirely, but it began to widen, and the beginning of a widening is not nothing. NASA also deployed 4 CubeSats from international partners to Earth orbit on that first day. Small satellites from cooperating space agencies released from the spacecraft before the translunar injection burn, part of a broader pattern of international collaboration that characterized the Artemis program. And then, on the second day of the mission, the moment that converted Integrity from an Earth orbital spacecraft into a deep space mission occurred with the firing of a single engine. The translunar injection burn lasted approximately 5 minutes and 49 seconds. With this firing of the spacecraft's service module engine, known as the translunar injection burn, Orion and its crew of NASA astronauts Reed Wiseman, Victor Glover, Christina Koch, and CSA astronaut Jeremy Hansen accelerated to break free of Earth's orbit and began the outbound trajectory toward Earth's nearest neighbor. 6 minutes of thrust is not a dramatic-sounding duration, but the physics it represents are profound. That burn changed the spacecraft's velocity enough to take it from a closed orbit around Earth a trajectory that would have brought it back to its starting point, to an open trajectory, one that would carry it away from Earth and toward the Moon. The spacecraft was no longer orbiting. It was traveling. The distinction matters. From the windows of Orion in those first hours after the burn, Earth would have appeared as it appears in the famous photographs. A sphere, smaller than a dinner plate held at arm's length, its blue and white resolving into the familiar patterns of ocean and cloud that no one who has seen it from space has ever described as anything other than extraordinary in its beauty and fragility. Reid Wiseman photographed it from one of Orion's 4 main windows shortly after the burn, the crescent of Earth framed against the absolute black of space beyond. 3 days of travel lay ahead. Stop here for a moment, because there is something important in those 3 days, not in the mission events, which were measured and careful and scientifically productive, but in the simple fact of the distance itself. The Moon is, on average, about 384,000 kilometers from Earth. That is close enough by astronomical standards that light crosses it in about 1.3 seconds. It is close enough that the Moon's gravity measurably affects Earth's oceans. It is close enough that you can see its craters with binoculars on a clear night. But it is still 3 days away by spacecraft. 3 days of travel across a void where there is no air, no sound, no temperature in any meaningful sense. Where the radiation environment outside the spacecraft is consistently hostile to biological tissue, and where the only thing standing between the crew and the vacuum of space is the aluminum, titanium, and composite shell of integrity. For 3 days, no geography passed beneath them. For 3 days, the nearest solid surface was first retreating Earth and then approaching the Moon. For 3 days, Wiseman, Glover, Koch, and Hansen occupied a volume of space that no human being had occupied in more than half a century. The vast, quiet region between Earth and Moon, where both worlds are visible simultaneously, where neither dominates the view, where you exist, for a few days, in genuine and absolute in-between. With astronauts aboard for the first time, engineers put Orion through a full in-flight evaluation. The crew tested the spacecraft's life support systems, confirming Orion can sustain humans in deep space. During several piloting demonstrations, crew members took manual control of the spacecraft, flying Orion to validate its handling and collect data that will guide future rendezvous and docking operations with human-rated landers during Artemis 3 and beyond. These were not mere demonstrations. They were the empirical confirmation that the systems designed on Earth, tested in simulators and arc jet facilities and vacuum chambers, actually performed as intended when a human being was sitting inside them in deep space, relying on them for life. Wiseman, Glover, Koch, and Hansen also supported scientific investigations to help NASA prepare astronauts to live and work on the Moon. These experiments, including the AVATAR investigation, which studies how human tissue responds to microgravity and the deep space radiation environment, and other human research performance studies, are gathering essential health data for long-duration missions. The deep space radiation environment is meaningfully different from what astronauts experience on the International Space Station, which orbits within Earth's protective magnetic field. Beyond that field, the cosmic ray flux is higher, the solar energetic particle events more dangerous, the accumulated dose over a lunar mission significantly greater than what ISS crew members receive. AVATAR and the other health investigations were not academic. They were building the database that will determine how long humans can safely spend on the Moon and, eventually, Mars. On April 4th, Christina Koch pressed herself to one of Orion's windows and looked back at Earth, now small enough to hold in the frame of a photograph. The image she captured, a blue-white crescent of Earth against total darkness, visible through the thick transparency of the spacecraft window, was released publicly and shared widely. It was, in miniature, the same revelation that Apollo 8 had delivered in December 1968. The Earth seen from far away, alone in the black, no larger from that distance than a marble in the palm of a hand, beautiful and impossibly thin-looking, its entire surface and all its billions of inhabitants compressed into a glowing disk. In those quiet 3 days between worlds, with Earth behind them and the Moon filling more of the window with each passing hour, the crew of Integrity were accumulating something that no training can fully impart: the psychological experience of genuine remoteness. The experience of being far from everything familiar, in an environment where nothing has changed in 4 billion years, where the ancient light of stars that were old before the Earth existed falls on your spacecraft without atmosphere to soften it, where the moon ahead grows not merely as a visual feature, but as a presence, a world, not an object, whose face you will soon see from closer than any human being has come in over 5 decades. Flight Day 2 is behind them. The translunar injection burn has fired. Earth orbit is behind them, receding. 3 days of silence and stars and growing anticipation lie between the Atlantic coast of Florida and the ancient stone of the far hemisphere. At 12:37 a.m. Eastern Daylight Time, on April 6th, the Orion spacecraft crossed a boundary that has no physical marker, but carries profound mechanical significance. Orion and the 4 humans aboard entered the lunar sphere of influence at 12:37 a.m. Eastern Daylight Time on April 6th, at the tail end of the 5th day of their mission. That marked the point at which the Moon's gravity had a stronger pull on the spacecraft than the Earth's. Up to that moment, Earth had been the dominant gravitational influence. Orion was, in the technical sense, an Earth-orbiting spacecraft that happened to be traveling away from Earth. After that moment, it was a Moon-orbiting spacecraft, or more precisely, a spacecraft falling toward the Moon, its trajectory bent by the Moon's gravitational field rather than Earth's. About an hour after entering the lunar sphere of influence, Artemis II mission specialist Christina Koch said, "We are now falling to the Moon rather than rising away from Earth." It is a precise description, and also a quietly extraordinary one: falling toward the Moon. A process that began more than 200,000 miles back, when the translunar injection burn first tilted the spacecraft's trajectory away from Earth's grip, was now entering its decisive phase. The Moon was not merely growing in the window, it was pulling. By early afternoon on April 6th, the Moon was close enough that its surface filled the window frame the way a landscape fills the windshield of a car. Features that had been specks in orbital photographs, the great dark plains of the near side, the bright ejecta rays of young craters, the highlands rising pale and complex around the edges of the Maria, were now resolving into 3-dimensional terrain. Shadows from crater rims reached across the surface at oblique angles. The terminator, the slowly moving boundary between lunar day and lunar night, divided the visible disk into a lit region of pale stone and a dark region where the surface disappeared into shadow. When Orion passed behind the Moon, starting at approximately 6:44 p.m., the mission would enter a planned communications blackout lasting about 40 minutes. This was not an emergency or a contingency. It was as predictable as the Moon's own geometry, and the crew and mission controllers had rehearsed it. As the spacecraft passed behind the far side, the Moon's entire mass would intervene between Orion and every antenna on Earth. The deep space network would lose signal, the crew would lose contact. For approximately 40 minutes, they would be completely, utterly alone, on the far side of the moon, in silence, with no way for anyone on Earth to know in real time what they were seeing or doing. You probably think that Artemis II was primarily an engineering test flight, with science as a welcome but secondary objective. This framing is not wrong. The mission documents are clear. The mission's primary goal was to validate the Orion spacecraft systems, crew operations, and mission procedures ahead of sustained lunar exploration in future Artemis missions. Artemis II astronauts were putting the Orion spacecraft through a series of planned tests to evaluate systems, procedures, and performance in deep space. They would conduct manual spacecraft operations and monitor automated activities, evaluate Orion's life support, propulsion, power, thermal, and navigation systems, perform proximity operations activities, assess habitability and crew interfaces, and participate in science activities, including lunar surface observations and human health studies that will inform science operations on future moon missions. But here is what that framing misses entirely. For a period of 7 hours above the moon, the astronauts would take high-resolution photographs and provide their own observations of the lunar surface, including areas of the far side of the moon never seen directly by humans. Those 7 hours made the Artemis II crew something that no mission specification document fully captures: the most sophisticated scientific instruments ever positioned above the far hemisphere. Not because they carried better cameras than orbiting spacecraft. They did not. Not because they had more processing power than robotic probes. They did not. But because the human eye and human brain, working together in context, with years of training in lunar geology, perceive things that no autonomous sensor system has yet been designed to perceive. The judgment to notice that a crater's interior shadow falls at an unexpected angle, suggesting a different slope than remote sensing indicated. The instinct to focus the camera on a particular color boundary, because the training says that color boundaries are compositionally meaningful. The ability to report in real time, not just what instruments measure, but what the experience of being there, looking at it, feels like. In the science evaluation room at NASA's Johnson Space Center in Houston, Dr. Kelsey Young and Dr. Trevor Graff, members of the Artemis II lunar science team supporting the mission from Earth in 2026, were listening to every observation the crew reported, comparing it against decades of orbital remote sensing data, building in real time a contextual picture that no remote mission could have constructed. A lively stream of science observations from the crew throughout the flyby was received with grins, nods, and lots of chatter in the science evaluation room, where lunar scientists were supporting the observations in mission control. The observation period was scheduled to begin at approximately 2:45 p.m. Eastern Daylight Time. 7 hours of continuous, systematic human observation of the moon, near side first, then the far side as they swept around the back, then the terminator region on the way out, and then the dark lunar surface during the solar eclipse that would occur as the moon moved between Orion and the sun. Before any of that, there was a record to break. The Artemis II crew of NASA astronauts Reed Wiseman, Victor Glover, and Christina Koch, along with CSA astronaut Jeremy Hansen, set the record for the farthest distance from Earth traveled by a human mission, surpassing the Apollo 13 record of 248,655 miles set in 1970. At their farthest point from Earth, the crew would be the 406,740 kilometers, 252,737 miles, above the Earth's surface, surpassing a record held for 56 years by Apollo 13. Apollo 13 held that record under circumstances no one would wish to replicate. A crippled spacecraft, an oxygen tank explosion, a crew improvising their way home on a free return trajectory they had not planned to use. The record had stood for 56 years, not as an achievement, but as a monument to crisis, to the outer limit of how far the problem had carried them before they could turn back. Now, integrity surpassed it, in a planned trajectory, in a functioning spacecraft, with a crew conducting systematic scientific observations of the world growing larger in their windows. The distance record passed at approximately 1:56 p.m. Eastern Daylight Time. Closest approach to the Moon? Pericynthian in the technical language, from the Greek words for near and moon, came later as Orion swept around the far side. On the second day of the test flight, with all systems on track, Orion's service module fired its main engine, placing the astronauts on a trajectory that brought them 4,067 miles above the lunar surface at their closest approach. 4,067 miles. Not close by the standards of low lunar orbit, where robotic orbiters fly at altitudes measured in dozens of kilometers, but close enough that the surface below filled the window like a landscape, detailed, textured, real in a way that no photograph transmitted from a robotic spacecraft can quite replicate, because the crew were not looking at a photograph. They were looking at the Moon. The free return trajectory that carried them there is worth understanding as a physical fact, because it is both elegant and profound. The mission follows a free return trajectory, using the gravity of the Earth and Moon to naturally guide the crew home. A free return trajectory is one in which the spacecraft, launched on a precisely calculated path, swings around the Moon and is bent back toward Earth by the Moon's gravity, without requiring any additional engine firing. The Moon's gravity does the work. If every engine on the spacecraft failed after the translunar injection burn, integrity would still have completed its loop around the Moon and returned to Earth. The crew could not have chosen this trajectory and then discarded it. The physics themselves would have brought them home. There is something worth dwelling on in that. The idea of 4 human beings entrusted not to a single engine or a single system, but to the fundamental mechanics of gravity itself. Their return guaranteed not by technology alone, but by the same force that has locked the Moon's face toward Earth for 4 billion years. The same force that makes the tides, the same force that shaped everything we have been discussing for the past several hours of this story. Gravity, patient and absolute, carrying them around the far side and back. The Moon's gravity was stronger now than Earth's. The Moon's surface filled the windows with ancient stone. The Moon's geological record, 4 billion years of silent accumulation, was about to be read by human eyes for the first time since the final Apollo crew departed in December 1972. At 2:45 p.m. Eastern Daylight Time on April 6, 2026, the 7-hour observation window opened. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen trained their cameras on the surface below and began to record. The observation period began at 2:45 p.m. Eastern Daylight Time on April 6, 2026, with the near side of the Moon below them, the face that has watched over every night in human history, now present not as a distant disk in the sky, but as a landscape, vast and detailed and close enough that its features had developed true depth. The crew approached from the western limb of the Moon, the edge that in the lunar evening sits closest to the setting sun. This angle placed the terminator, the boundary between lunar day and lunar night, across a broad swath of the visible terrain, and low-angle sunlight does something to lunar topography that overhead illumination cannot. When the sun sits near the horizon, every raised rim, Every impact melt sheet, every wrinkle of ancient compression in the crust, casts a shadow extended to extraordinary length across the surface below it. Topography that would be invisible in flat overhead light becomes bold and three-dimensional in the raking illumination of a near-horizontal sun. They documented the topography along the terminator, the boundary between lunar day and night, where low-angle sunlight casts long shadows across the surface, creating illumination conditions similar to those in the South Pole region, where astronauts are scheduled to land in 2028. This was not incidental. The Artemis 3 mission, the one that will, for the first time since December 1972, put human beings back on the lunar surface, is targeted for the Moon's south polar region, a terrain of permanent shadow and extreme illumination angles, where water ice is thought to persist in the floors of craters that have not seen direct sunlight in billions of years. The terminator conditions the Artemis 2 crew was observing in April 2026 are the conditions Artemis 3 astronauts will work in. Every shadow captured, every crater rim measured, every ejector blanket examined in that raking light becomes data for the crews who will follow. They photographed Reiner Gamma, the enigmatic surface swirl on the near side Oceanus Procellarum, that bright, mysterious swirl the origin of which scientists are still trying to understand, a region where the surface has been brightened by processes that may involve the interaction of ancient volcanic gases with the solar wind, leaving a magnetic anomaly that deflects the particles that normally darken lunar soil. They photographed Glushko Crater, a bright young impact structure known for the long, brilliant streaks of excavated material that shoot outward from its rim for as far as 500 miles in every direction, evidence of a relatively recent and energetic impact that ejected pristine material from beneath the surface, material that has not had the billions of years of exposure to solar wind that darkened everything around it. They photographed the terminator zone in the southern highlands, where the ancient pre-mare terrain exists almost unchanged from the days when the Moon was young and the solar system was still assembling itself. From the Science Evaluation Room in Houston, Dr. Kelsey Young and Dr. Trevor Graff were receiving the observations in real time, matching what the crew reported against the orbital remote sensing datasets and processing the implications as each new image arrived. A lively stream of science observations from the crew throughout the flyby had been received with grins, nods, and lots of chatter in the Science Evaluation Room, where lunar scientists were supporting the observations in mission control. What the crew reported was not simply what the cameras captured. It was richer than that. They reported color gradients across the Maria that suggested compositional variations too subtle for current orbital spectrometers to resolve with confidence. They reported the way the texture of crater ejector blankets changed with distance from the impact point, offering qualitative data about energy dispersal that models had predicted, but never directly confirmed from this perspective. The crew reported color nuances, which will help enhance scientific understandings of the Moon. Color is easy to underestimate as a scientific tool. It seems imprecise, subjective, the kind of thing you measure with an instrument rather than an eye. But trained human observers, like trained wine tasters or trained radiologists, perceive color distinctions that calibration curves and spectral models do not always capture. The specific shade of gray-brown in a particular ejector field, the subtle blue tinge of a pyroclastic deposit relative to its surroundings, the way a specific crater floor appears darker than the surrounding terrain, in a way that suggests a compositionally distinct impact, melt rather than simple crater depth. These are the kinds of observations that orbital spectrometers approximate, and human eyes, in context, verify. As the spacecraft moved around the limb of the Moon, transitioning from the visible near side to the hidden far hemisphere, the crew was positioned for one of the most photographed moments of the mission. At 6:41 p.m. Eastern Daylight Time, 4 minutes before the planned communications blackout, the crew watched Earth set below the lunar horizon. Earthset captured through the Orion spacecraft window at 6:41 p.m. Eastern Daylight Time, April 6, 2026, during the Artemis II crew's flyby of the Moon. A muted blue Earth with bright white clouds sets behind the cratered lunar surface. The dark portion of Earth is experiencing nighttime. On Earth's day side, swirling clouds are visible over the Australia and Oceania region. In the foreground, Ohm crater has terraced edges and a flat floor, interrupted by central peaks. This is the image that most of the world would see first, in the hours after the flyby data was released. Earth, impossibly small and impossibly beautiful, dropping behind the crater-pocked horizon of the far side. The rim of Ohm crater in the foreground, with its terraced walls and central peaks that rose from the floor when the impact liquefied the rock, and it splashed upward before freezing in mid-gesture. Central peaks form in complex craters when the lunar surface, liquefied on impact, splashes upwards during the crater's formation. That geological explanation, the frozen splash, the rock briefly liquid and then stone again, is visible in that single photograph as a reminder that even the Moon's most serene-looking features are records of violence, of energy so concentrated that it momentarily converted solid rock into fluid, and then let physics take over. Close to the lunar limb, as the spacecraft swept toward the far hemisphere, the crew captured the close-up view that many lunar geologists had been waiting for. Vavilov crater on the rim of the older and larger Herzsprung Basin. Vavilov, a relatively young impact structure sitting atop one of the far side's largest ancient basins, offered scientists a rare opportunity to study two different generations of impact geology in a single field of view. The fresh, sharp-edged walls of the younger Vavilov against the worn, degraded topography of the ancient Herzsprung, which formed more than 3 billion years ago and has been modified by subsequent impacts ever since. By comparing the topography of the two craters, the crew's observations will help scientists gain insight into how lunar features evolve over geologic timescales. That is, in miniature, what the entire Farside Science program is about: understanding geological time through the comparison of features at different stages of degradation. The Moon is an outdoor museum of impact geology, its exhibits preserved across timescales that no museum on Earth can approximate. Along the Terminator in the Farside Highlands, the crew captured images of Joule Crater, Birkhoff Crater, and Stebbins Crater, three ancient structures whose rims cast shadows across the battered terrain below. These are not famous craters. They are the ordinary geology of the far side, old, worn, overlapping, sitting on crust that solidified billions of years ago and has scarcely changed since. Photographing them under Terminator lighting, the crew was building a dataset that refinements to crater counting and age estimation methods will use for years. Because the age of a surface is often estimated from the density and degradation state of its craters, and having human-observed, in-context images under known illumination conditions is an anchor that improves the calibration of every orbital dataset taken before and after. The near side was familiar from 1,000 photographs. The near side was the face of 100 myths and navigation systems. The near side was about to give way to something no human being had looked at from this distance with their own eyes. At 6:44 p.m. Eastern Daylight Time, when Orion passed behind the Moon, the mission entered a planned communications blackout lasting about 40 minutes. The spacecraft passed behind the far hemisphere. The Deep Space Network lost signal. mission control in Houston went quiet, and 4 human beings found themselves in a position that no human being had occupied since the Apollo astronauts, on the far side of the moon, completely and utterly out of contact with Earth, with the moon's entire mass intervening between them and every person, every institution, every signal transmitter on the planet. Similar blackouts had occurred during the Artemis 1 and Apollo missions, and were expected when using an Earth-based communications system. The technology to maintain contact during such a blackout exists. A relay satellite in the right orbit can see both the far side surface and Earth simultaneously, as China's Queqiao-2 demonstrated for the Chang'e 6 mission. But Artemis 2's trajectory did not use such a relay, and so for approximately 40 minutes, the crew was on their own. There was no signal from Earth. There was no voice from mission control. There was only the 4 of them and the moon below at 4,067 miles, and the total absence of the ambient noise that radio communications create, and the far side of the moon, ancient, pale, battered, creep-poor and water-depleted, and geologically quiet for billions of years. Visible through the windows in the sharpest detail, any human being had seen it from space. Around 7 p.m. Eastern Daylight Time, Orion reached Pericynthian, closest approach. On the second day of the test flight, Orion's service module had fired its main engine, placing the astronauts on a trajectory that brought them 4,067 miles above the lunar surface at their closest approach. At that altitude, the moon below them was not an abstraction. It was a world. The curvature of the horizon was visible, the surface stretching away in all directions, the great sweeping blandness of the far side highlands, broken only by the geometric precision of impact craters, some small and sharp, geologically young, others vast and degraded, ancient enough that subsequent impacts had modified their rims and floors beyond recognition. 2 minutes after closest approach, the distance record fell. The Artemis 2 crew set the record for the farthest distance from Earth, traveled by a human mission, surpassing the Apollo 13 record of 248,655 miles set in 1970. The crew reached 252,756 miles from home at their farthest distance from Earth. For 56 years, the Apollo 13 record had stood, not as a triumph, but as the outer limit of a catastrophe, the farthest point a crippled spacecraft had carried its crew before the free return trajectory began bringing them home. Now, in a functioning spacecraft, on a planned trajectory, with a crew conducting systematic scientific work, integrity surpassed that distance. The record passed quietly, without ceremony, because the crew were occupied with what was outside the windows. When Orion emerged from behind the moon at approximately 7:25 p.m. Eastern Daylight Time, the crew witnessed an Earthrise as Orion emerged from behind the moon, moments before the Deep Space Network reacquired the spacecraft's signal. Earth rose above the far horizon of the moon just as communications were restored. In the sequence of images the crew captured in those minutes, Earth rising above the crater-pocked limb, the planet's small and crescent lit against the darkness, the echo of Apollo 8's Earthrise photograph from December 1968 was unmistakable and deliberate. The same geometry, the moon's surface in the foreground, Earth rising beyond it, the distance between them made visible by the juxtaposition. The first words transmitted from Integrity when communications were restored came from Christina Koch, mission specialist, record holder for the longest single spaceflight by any woman in history, a person who had spent 328 consecutive days on the International Space Station developing an understanding of how the human body and human mind adapt to the conditions of space. What she said was, "It is so great to hear from Earth again." Not a scientific report, not a systems status update, a human statement, direct and unadorned, from someone who had just spent 40 minutes on the far side of the moon with no connection to the world she came from. It is so great to hear from Earth again. 7 words that compress more meaning than most speeches. The observation period continued. Behind them now was the far side, photographed, observed, catalogued in 7,000 images and dozens of hours of recorded observations. Ahead was the solar eclipse. Toward the end of their observation, starting at approximately 8:35 p.m., the crew would witness a solar eclipse from space as Orion, the Moon, and the Sun aligned. The astronauts would see the Sun disappear behind the Moon for nearly an hour. From Orion's position in deep space, the Moon appeared large enough, its angular diameter sufficient from that proximity, to completely cover the Sun. On Earth, total solar eclipses are brief, lasting a few minutes at most, because the Moon's shadow sweeps across Earth's surface at orbital speed, and any given location on the ground is in totality for only a short window. From Orion's vantage, moving with the Moon, the geometry sustained for far longer. The crew's perspective, the Moon appeared large enough to completely block the Sun, creating nearly 54 minutes of totality and extending the view far beyond what is possible from Earth. 54 minutes of totality. 54 minutes during which the Sun's corona, its outermost atmosphere, normally invisible behind the overwhelming brightness of the solar disk, glowed around the darkened Moon in a halo of structured light. The corona's shape is a record of the Sun's magnetic field, long streamers following magnetic flux lines, bright plumes where field lines reach outward, dark regions where material is flowing inward. From the ground, total eclipses last too briefly to study the corona in detail. From Orion's position, 54 minutes of totality offered an observation opportunity that has no parallel in Earth-based solar observation. From the crew's perspective, the Moon appeared large enough to completely block the Sun, creating nearly 54 minutes of totality. We see a glowing halo around the dark lunar disk. The science community is investigating whether this effect is due to the corona, zodiacal light, or a combination of the two. This uncertainty is itself scientifically significant. The glowing halo that appeared in the eclipse images was not definitively identified as a solar corona alone. Zodiacal light, the faint glow produced by sunlight reflecting off dust distributed along the plane of the solar system, can overlap with corona observations when the viewing geometry is right. Distinguishing between the two in the images captured by the Artemis II crew requires careful analysis of the halo's structure and spectrum, and that analysis was ongoing in the weeks following the mission. Also visible were stars, typically too faint to see when imaging the Moon. But with the Moon in darkness, stars were readily imaged. Stars visible next to an eclipsed Moon, photographed from beyond the Moon's orbit. Venus bright on the left edge of the image, its reflected light competing for attention with the corona's glow. The faint glow of Earthlight on the near side of the Moon, visible as a pale luminosity on the left face of the dark disk, sunlight reflected from Earth's oceans and clouds, traveling 400,000 kilometers to illuminate the Moon's near hemisphere from the other direction. And then, against the darkened lunar surface, 6 times during the eclipse observation, something appeared that had not been planned for, had not been scripted, would not have been observable from any previous crewed mission above the Moon. The crew also reported 6 meteoroid impact flashes on the darkened lunar surface. 6 flashes, 6 brief, brilliant points of light against the unilluminated surface of the moon. 6 moments when a piece of the solar system's ancient debris, a meteoroid, a fragment of rock or metal traveling at tens of kilometers per second, struck the moon hard enough that the kinetic energy of its impact converted briefly into light, visible across thousands of miles to 4 human eyes watching from a spacecraft. 6 times the ancient moon was struck while they watched. 6 times the ongoing bombardment that has shaped the lunar surface for 4 billion years was directly observed by a human crew. The crew would use the opportunity to watch for flashes of light from meteoroids striking the surface, which could offer insight into potential hazards on the moon. The hazard assessment value is real and practical. Artemis 3 astronauts will be on the lunar surface. Meteoroid impact flashes, observed over time, help calibrate the current impact rate and inform the design of habitats and spacesuits for people who will be standing in the environment the impacts threaten. But there is something beyond the practical in those 6 flashes, something that speaks to the scale of time the lunar surface represents. The moon has been struck by objects like this continuously for 4.5 billion years. The craters the crew photographed, Vavilov, Ohm, Yule, Birkhoff, Stebbins, Herzsprung, and the vast wound of the SPA itself, are all the products of the same process that produced those 6 flashes, simply operating over longer timescales and with larger impactors. The moon's entire surface is a record of impacts, layer upon layer upon layer, the most recent sitting on top of the oldest, each one a data point in a continuous bombardment history stretching back to the formation of the solar system. The crew of Integrity watched the moon being struck 6 times in 1 hour of observation. Across the 4.5 billion years of the moon's history, if the average impact rate is even 1,000th of what they witnessed, the cumulative number of impacts reaches into the billions. They also proposed names for 2 lunar craters, a tradition that connects astronauts to the geography they have observed directly, a way of saying, "We were here, we looked at this place is now part of our story, as well as the moon's." After their 7-hour lunar flyby, the crew received a congratulatory call. The observation period was complete. The scientific data, more than 7,000 images of the lunar surface and a solar eclipse, observations of Earthset and Earthrise, records of impact craters and ancient lava flows, and surface fractures and color variations across the terrain, Terminator topography data for Artemis 3 planning, and the 6 meteoroid impact flashes, was now in the hands of scientists on Earth who would spend months and years extracting its full meaning. Stop here for a moment. Take stock of what has been gathered. During their April 6th lunar flyby, the astronauts captured more than 7,000 images of the lunar surface and a solar eclipse, during which the moon blocked the sun from Orion's vantage point. The imagery includes striking views of Earthset and Earthrise, impact craters, ancient lava flows, our Milky Way galaxy, and surface fractures and color variations across the lunar terrain. Pair that with the Chang'e 6 samples, the 1,935.3 grams of far-side basalt, 2.83 billion years old, creep poor, extraordinarily dry, and pair both with the Grail crustal thickness map and the competing theories for the dichotomy's origin, and what you have is the most complete picture of the far-side moon that has ever existed. A picture with a question at its center that has not yet been answered. But a picture clear enough to ask the question more precisely than it has ever been asked before. Now we turn to that question, not as a technical problem in planetary geology, but as a philosophical revelation about what the moon tells us about everything beyond it. There is a moment in the study of any deep problem when the data you have accumulated reaches a certain weight, and the weight collapses the previous framing of the question entirely. It does not answer the question so much as it reveals that the question was the wrong shape. You were asking something too small. The answer that emerges is larger than the question that prompted it, and once you see it, the original question seems naive in retrospect. Not wrongly asked, but inadequately ambitious. What caused the lunar dichotomy? That was the question. What made the moon's near side different from its far side? That was the question for 67 years. And here is where everything that has come before inverts. What if the lunar dichotomy is not a lunar problem at all? Consider Mars. The planet that most resembles Earth in its geological history, the world whose surface preserves, like the moon, a record of conditions that terrestrial erosion and plate tectonics have erased on our own planet. Mars has its own hemispheric dichotomy. The northern lowlands of Mars are lower in elevation, younger in age, smoother in texture than the ancient southern highlands. The same basic picture as the moon. One hemisphere old and battered, the other resurfaced and topographically distinct. Scientists studying the Martian dichotomy have proposed the same range of explanations they have proposed for the moon. Giant impacts, internal differentiation, differential cooling rates in the early planet. Consider Earth itself. The planet we stand on has a bimodal crustal distribution. The dense basaltic rock of the ocean floors, thin and dark, and the less dense granitic rock of the continents, thick and pale. This is not a random arrangement. It reflects the way the early Earth differentiated, how the first crust formed, and was then repeatedly processed by the mantle convection cycles that continue today. The same fundamental tension between a dense, processed, reprocessed surface and a lighter, primordial crust that defines the moon's dichotomy is also present in a more evolved and complex form in Earth's own geological structure. What if every rocky planet in the inner solar system goes through something like this? What if the formation of a rocky world almost inevitably produces a hemispheric asymmetry, some version of the two-faced moon, driven by the same set of processes? Giant impacts concentrating materials, differential cooling rates in a tidally locked or rapidly rotating body. The random violence of the early solar system preferentially striking one region of a world and altering its geological destiny. What if the moon, precisely because it stopped evolving geologically so early in its history, has preserved the clearest record of a process that reshaped every rocky body in this part of the solar system, and then was erased by the subsequent geological activity that made those bodies interesting in other ways? What does that mean about what we cannot know? We cannot know what the early Earth's mantle looked like in the first 100 million years after its formation, not because the instruments do not exist to measure it, but because the evidence itself has been destroyed. Plate tectonics has recycled every piece of the early crust. Volcanism has overprinted the original chemical distribution with billions of years of subsequent modification. The geological archive that the moon preserves with such fidelity, the primordial crust chemistry, the impact record extending back 4 billion years, the creep-poor far-side highlands that represent something close to what the raw lunar mantle produced, has no equivalent on Earth. It is not that we lack the tools to read it. It is that the text no longer exists. There is a category of knowledge about our own planet's formation that is simply and permanently beyond our reach, not at the frontier of current understanding, but beyond any understanding, because the material that could answer the question has been transformed beyond recognition. This is not a failure of science. It is an epistemological boundary, a place where the universe has imposed a limit on what can be known, regardless of how sophisticated the instruments become or how carefully the mission is planned. We cannot retrieve Earth's first 100 million years. We cannot touch the original crust. We cannot know what the early Earth's interior looked like. We can, however, read the moon. And reading the moon, which is what every mission from Lunar 3 to Chang'e 6 to Artemis 2 has been doing in their different ways, is reading a document that was written at the same time as the early Earth, from the same material, under the same catastrophic conditions. The moon did not form independently of Earth. It formed from Earth, from the debris of the same collision that shaped both worlds, that distributed their shared material across the orbital neighborhood and let gravity sort it into the two bodies we now call Earth and Moon. What the moon's geological record preserves is, in a very specific and scientifically meaningful sense, a version of Earth's early geological record. The record that Earth erased. Does that mean the lunar dichotomy is actually Earth's story, not the moon's? Does it mean that the concentration of creep on the near side, those radioactive, heat-producing elements that drove 4 billion years of volcanic difference between the two hemispheres, tells us something specific about how the early Earth's interior sorted its materials before plate tectonics took over and rearranged everything? Does it mean that if we could fully understand the SPA impact and trace the heat plume that some researchers believe carried creep from the far side mantle to the near side, we would understand something about how giant impacts in the early solar system reshaped not just their immediate targets, but the chemical distributions of entire worlds? Is the moon's near side volcanic, not because of some lunar-specific quirk, but because the entire inner solar system, in its first billion years, was so violent, so continuously bombarded, so constantly reshuffled by impacts of astonishing energy, that any rocky body that solidified during that period inevitably bears the marks of that violence as its deepest geological identity? Are the 6 meteoroid flashes the Artemis 2 crew watched during the eclipse, those brief, brilliant punctuations on the darkened lunar surface, the present-day whisper of a process that, 4 billion years ago, was so loud it could be heard across an entire hemisphere? How many of the craters the crew photographed during the 7-hour flyby exist because of impacts that also struck Earth, that may have delivered the water and carbon and organic compounds that made life on Earth possible in the first place? What will the Artemis 3 astronauts find when they stand on the lunar South Pole in 2028, in the shadowed craters where water ice is expected, reading the geological record in person rather than through a window thousands of miles up? And what does any of this mean for the question that was never really about the moon? The question that was always underneath the geology and the orbital mechanics and the competing theoretical models about us. The moon is our only witness to our own beginning. The Earth we live on has no memory of its infancy. Its early crust is gone, erased by the very geological activity that makes it habitable. But the moon remembers. It was there. It was formed from the same violence, and it kept the record. What did it keep? What is written in those far side highlands, in that pale anorthosite crust, in those creep-poor, water-depleted, ancient and unmodified rocks that Chang'e 6 brought back and Artemis 2 surveyed, and every mission since 1959 has been, in one way or another, approaching? Something about the beginning, something about the moment 4.5 billion years ago, when a planet and its moon formed simultaneously from the same catastrophe and set off on the different paths that led, eventually, to the world you are resting in right now. The world that became habitable. The world that became biological. The world that became conscious and then curious, and then sent 4 people in a spacecraft named Integrity around the back of its companion world to look. Once you see the lunar dichotomy this way, not as a specific anomaly on a specific world, but as the oldest, clearly readable record of how rocky planets form their identities, the entire history of lunar science changes its meaning. Luna 3's grainy photographs in 1959 were not just the first images of a geologically different hemisphere. They were the first glimpse of a message that Earth's own geology had long since burned. Grayle's crustal thickness measurements were not just numbers on a planetary map. They were a quantitative record of a process that may be universal to rocky world formation. Chang'e 6's far-side samples were not just 2 kilograms of lunar regolith. They were the first physical samples from the oldest, clearly readable archive of planetary formation in the inner solar system. And the Artemis II crew, sweeping around the far hemisphere at 4,067 miles above the ancient surface, photographing and observing and reporting their color nuances and texture observations and 6 meteoroid flashes. They were not simply test pilots validating a spacecraft. They were readers, returning to a document that had waited 4 billion years for someone to look at it carefully. What they found there, and what the science now says about what they found, is what the remaining pages of this story are about. Picture yourself inside the Orion spacecraft on April 7, 2026. The 7-hour observation window closed the night before. The moon, which filled the windows for that extraordinary afternoon and evening, is already receding behind the spacecraft. Not dramatically, not all at once, but with the patient persistence of gravitational mechanics, shrinking back toward the scale of something you look at, rather than something you exist inside. Yesterday, it was a world, filling the frame, its craters and highlands resolved into genuine topography, its surface textured and 3-dimensional, and close enough that your mind kept reaching for depth. Today, it is a sphere again. It is the moon again. Earth is ahead, growing. The return journey began on April 7th at approximately 1:25 p.m., when Orion exited the lunar sphere of influence at approximately 1:25 p.m., at a distance of 41,072 miles from the moon. That moment marked the transition from moon-dominated space back to Earth-dominated space. The mirror image of the threshold crossed 3 days earlier, when the moon's gravity first outweighed Earth's. The same boundary, crossed in the opposite direction, with 4 people returning from somewhere no human being had been in more than half a century. The physics was the same as the outbound journey, but the crew was different. Something had happened during those 7 hours above the moon that had not been possible to fully anticipate in the training simulations, in the geological flashcard sessions, in the field exercises, in Iceland's lunar analog volcanic highlands. They had been there. They had looked at it. And whatever that means for a human mind, to have looked at the hidden face of the world that has watched over every night in human history, it does not fully resolve itself in the hours immediately afterward. Stay with that for a moment, without adding more information. This is not the time for new data. It is the time to feel the weight of what has already been said. The crew said in one interview that the thing they will miss most about their time in space is each other. They had been training together for their mission for the past 3 years. 3 years of shared preparation for something unprecedented, followed by 10 days of absolute mutual dependence. Because in deep space, in a pressurized capsule hundreds of thousands of miles from any other human being, the 4 people you are with are, temporarily, your entire world. They knew each other's habits, each other's voices, each other's way of falling silent when something outside the window demanded attention. When the communications blackout ended, and Coke said it was so great to hear from Earth again, she meant Houston. She meant mission control. She meant the familiar voices of the people managing the spacecraft from the ground. But she also meant something larger. The sound of the world she came from, the world she was returning to, the world that was growing slowly in the window ahead. The moon's two faces are still there. The fact that a crew flew past one of them does not change its geological reality. The ancient highlands of the far side, pale, battered, creep-poor, composed of anorthosite crust that solidified 4 billion years ago from a magma ocean that no longer exists, are exactly as they were before April 6, 2026. The South Pole-Aitken Basin still plunges 8 kilometers below the surrounding terrain. The craters that Wiseman, Glover, Koch, and Hansen photographed are still there. Vavilov still sits on the rim of the ancient Hertzsprung Basin, its walls casting long shadows in the oblique lunar light. Ohms still rises from the far side highlands, with its terraced interior and central peaks frozen in mid-splash. Joule and Birkhoff and Stebbins still mark the Terminator Zone, their ancient forms wearing the patient degradation of 3 billion years of subsequent impacts. Nothing changed because human eyes looked at it. But the relationship between those geological facts and human understanding has changed, and that change is irreversible. Shades of browns and blues that can be picked out with human eyes can help reveal the mineral composition of a feature and its age. That was what Dr. Kelsey Young had described in advance of the flyby, the specific scientific value of human color perception in context, the ability to distinguish subtle variations that orbital spectrometers approximate from hundreds of kilometers, and that cameras capture in the particular spectral sensitivity of their sensors. The crew delivered. The science evaluation room, where the observations arrived in real time, received a continuous stream of geological reporting that no robotic mission had been able to generate. Not because the instruments were inadequate, but because the human observers were using an instrument that has been trained by evolution and geology coursework and 3 years of mission preparation to notice things that algorithms are still learning to see. Dr. Kelsey Young had put it plainly before the mission. We're looking for the crew to call out any of those subtle color nuances, especially on the parts of the far side that have never been seen before by human eyes. And they did. The color reports from the crew are now part of a dataset that will inform the interpretation of every orbital observation made of those regions before and after the mission, a contextual anchor, a human calibration point in a field of instrumented data. As crew reports were received, the science team was updating the observation plan based on their follow-up questions and sending up new guidance to the crew. This is what human presence enables that robotic presence cannot: real-time scientific dialogue. The ground team could ask the crew to look again at something, to describe a particular feature from a slightly different angle, to report whether a color boundary they had noticed in remote sensing data corresponded to a texture boundary visible from the spacecraft's altitude. The conversation between the crew and the scientists in Houston over those 7 hours was a scientific instrument in itself, more flexible, more contextual, more responsive than any automated system. The question that has lived at the center of this story: why the two faces of the moon are different, what event or series of events in the first 100 million years of lunar history set one hemisphere on a path that the other did not follow, has not been answered by Artemis II. It has been more precisely framed. The high-resolution Terminator observations add detail to the crustal structure models. The color and albedo reports, albedo being the scientific term for a surface's reflectivity, the proportion of incoming light it bounces back rather than absorbs, give geochemists new data to work with in calibrating the spectral databases that underpin composition mapping. The meteoroid flash observations add a present-day impact rate data point that helps constrain the history of past bombardment rates. But the dichotomy remains, in the most honest scientific language, unresolved. The mystery that began with Luna 3's grainy photographs in 1959, that deepened with Grail's precise crustal maps, that gained its first physical far-side samples from Chang'e 6's 2 kilograms of ancient basalt, is still open. It is closer to an answer. It may be much closer. The convergence of evidence from multiple missions and multiple research programs is beginning to produce a picture that some scientists believe will, within the next decade, be definitive. But as of the spring of 2026, no single theory accounts for all the data, and the honest position is still that the origin of the lunar dichotomy is uncertain. There is something both melancholy and correct about that. The Moon has kept its deepest geological secret for 4 billion years. It is patient in a way that human science has only recently begun to match. Every answer we extract from it is earned at the cost of decades of careful work by hundreds of scientists and engineers and astronauts and technicians across multiple countries and multiple generations. The answer, when it comes, will not arrive easily. It will arrive the way the Moon's own geological history arrived, slowly, incrementally, through the accumulation of evidence that each generation adds to what the previous generation established. The Artemis II crew, returning across the void toward Earth, had added their layer. 7 hours of human observation, more than 7,000 images, 6 meteoroid flashes, a solar eclipse lasting 54 minutes, with a corona whose composition is still being analyzed, color nuances that will take months to fully interpret, geological context that no orbital dataset alone can provide. They had been the most precisely prepared human observers ever placed above the far side of the Moon. They had attended classes with the scientists, blazing through flashcards to understand lunar geography, handled rocks to get a better grasp of geology, and even trained like field scientists in the Icelandic highlands, a great lunar analogue on Earth. And they had delivered what their preparation promised. Look at the Moon that way for a moment. Look at it not as an object in the sky, but as the accumulated target of 67 years of human inquiry, of missions planned and flown and analyzed, of theories proposed and tested and revised, of rock samples analyzed in laboratories from Houston to Beijing to Moscow. 4.5 billion years of geological quiet, waiting. 67 years of human reaching, approaching. 10 days of human presence in its vicinity, looking. And the Moon, unchanged, holding what it always held, neither yielding nor withholding, simply existing in the particular condition of being ancient and measurable, and still not fully understood. The crew of Integrity would splash down in the Pacific Ocean off the coast of San Diego on April 10, 2026. They would be helped out of the capsule by Navy divers and lifted by helicopter to the USS John P. Murtha. And they would undergo medical evaluations, and they would return to Houston, and the photographs and data they had gathered would begin the long process of scientific analysis that would continue for years. The mission, 10 days from launch to splashdown, was complete. What began is longer than 10 days. 58 years before Artemis II swept around the far hemisphere, a crew of 3 human beings made the same journey for the first time, under conditions of profound uncertainty about whether the mission would succeed and genuine existential risk to the crew. Their names were Frank Borman, James Lovell, and William Anders, and their mission was called Apollo 8. They launched on December 21, 1968, on a Saturn V rocket, taller than the Space Launch System and producing about 7.6 million pounds of thrust at liftoff, a rocket that shook the ground for miles. They reached the Moon on December 24th, entered lunar orbit, and became the first human beings to see the far side of the Moon directly, with their own eyes, from a distance of 70 miles above its surface. The Apollo 8 astronauts provided the first and most detailed human observations of the far side of the Moon, all while testing systems and procedures that became critical to the success of future Apollo missions. During their time in orbit, the Apollo 8 astronauts observed and documented key geologic features, such as Tsiolkovsky Crater, the Sea of Tranquility, and the Taurus Littrow Mountains. They circled the Moon 10 times on Christmas Eve and Christmas Day, 1968, looking down at a surface that no human being had ever seen from close range, reading their geological observations into the radio, and becoming, for a few days, the most remote human beings who had ever lived. And then, William Anders pointed his Hasselblad camera at the lunar horizon and saw something rising above it. Earth. The photograph he took, that small, luminous blue and white sphere rising above the grey and airless lunar surface, became one of the most reproduced and influential images in human history. It is called Earthrise. It showed for the first time what humanity looked like from the outside. Not a civilization, not a nation, not a species, but a single small object suspended in the void, its entire surface visible in one frame, its blue oceans and white clouds, and the thin film of atmosphere that makes it habitable, all compressed into something that fit comfortably in the palm of a hand. Many historians of the environmental movement trace its modern form, in part, to that image, to the visceral recognition that Earth is not an infinite background against which human activity unfolds, but a specific, finite, fragile object in a very large and very indifferent universe. That was December 1968. Those observations ultimately helped mission engineers plan for future Apollo missions and helped scientists better understand the stark geologic differences between the near and far side of the Moon. And then the Apollo program ended, and the human presence near the Moon ended with it. And for 53 years, the Moon returned to being something seen from a distance, studied by robots and orbiters and remote sensing instruments, approached but not inhabited, known but not visited. When Artemis II's crew captured the Earthsat image, Earth dropping below the lunar horizon as they swept around to the far side, something inverted in a way that carries more weight than the simple geometry of it. Apollo 8 saw Earthrise, Earth returning from behind the Moon, coming back into view, the world made visible again after the darkness of the far side. Artemis II saw Earth set, Earth disappearing below the far side horizon, receding from view, the world letting go of its travelers as they crossed into the region of absolute silence and ancient stone. One mission saw the Earth coming. The other saw it going. One marked a beginning. The other marks a return. But a return that is also something else, something that takes a different shape when you look at it from where we now stand. Apollo 8 went to the Moon with almost no scientific context for what the far side was. They knew it was different from the near side. Lunar 3's photographs were 9 years old by then. But the structural details, the crustal thickness asymmetry, the creep distribution, the competing theories for the dichotomy's origin were either unknown or in the earliest stages of formulation. They were flying in the dark, in more than the literal sense. What they saw without the interpretive framework that 66 more years of research would eventually provide. Artemis II went to the Moon carrying all of it: the Grail data, the Chang'e 6 samples, the 3 competing theories for the dichotomy. Dr. Kelsey Young's catalogue of 35 geological features carefully selected for their scientific significance. 3 years of geological training that included, at least for one of the crew, a working ability to identify the difference between ancient anorthosite crust and impact, melt by their color and texture under varying illumination conditions. We're able to ask more intelligent questions because of what Apollo gave us, Young said before the mission. Apollo asked, "What is the far side?" Artemis too asked, "Why is the far side, and what does its nature tell us about the beginning of the world?" This is not a small shift. It is the difference between cataloging and understanding, between seeing something for the first time and returning to it, knowing what questions to bring. The two missions bracket an era. Between Apollo 8 and Artemis, too lies 58 years of lunar science, all of it motivated in various ways by the recognition that the moon is not simply a destination or a navigation landmark or a symbol in human mythology. It is a physical record, the oldest, clearly readable physical record of the conditions that existed in the inner solar system in the first 100 million years after the sun's formation. A record that Earth itself has destroyed, not through malice or indifference, but through the very geological activity that made Earth a living world. The plate tectonics, the volcanism, the ocean chemistry, the biological transformation of the atmosphere that collectively constitute the life history of our planet, and collectively erased the geological memory of its infancy. The moon remembers what Earth cannot. That is the sentence at the center of everything this story has been building toward, and it deserves to be held for a moment before what follows it is said. The moon remembers what Earth cannot. It remembers the first crust. It remembers the conditions of the magma ocean. It remembers the bombardment record from the first billion years of solar system history in the form of craters that have not been erased. It remembers the asymmetry, the different chemical identity of the two hemispheres that was imprinted on the moon's structure in its first tens of millions of years and has not been significantly altered since. The near-side face you have known your whole life, with its dark maria and pale highlands, and the pattern that has anchored human imagination since before written language, is a record of that asymmetry's consequences. The volcanism that creep heat sustained, the lava floods that covered the great impact basins, the geological renewal that gave the near side a younger and more complex surface, and the far side face that the Artemis II crew saw above them through the windows of integrity, that ancient and battered and creep-poor terrain that Chang'e 6's samples described in chemical terms. That face is the other side of the same record, the side that did not get the heat, the side that did not get volcanism, the side that simply preserved in stone what the beginning looked like. Consider what that means for the question of who we are and where we come from. The Earth that produced you, the specific planet with the specific chemical composition and the specific temperature range and the specific combination of water and atmosphere and geological activity that made biological life not only possible but persistent across 4 billion years, is the product of processes that began in the same catastrophic collision that made the moon. The impact that formed the moon was also the impact that reshaped the early Earth, delivering to it the angular momentum that gives it its 24-hour day, the energy that drove its early volcanic activity, possibly the volatile compounds that seeded its oceans. Earth and moon are not merely neighbors. They are siblings of a violence so extraordinary that calling it formative seems insufficient. The moon's geological record is, in the most literal sense, a partial record of Earth's origin story, a piece of the original text that survived because it was ejected from the main narrative before the editing began. Earth is the novel. The moon is the discarded draft. And the discarded draft preserves sentences that the novel revised away. During the Apollo 17 mission, the program's final crewed venture to the lunar surface in 1972, NASA astronaut and geologist Harrison Schmitt spotted orange soil and collected a sample. Once back in orbit, the Apollo 17 crew saw the same orange hue on the lunar surface, which later revealed that volcanic processes were active on the moon's surface for longer than expected. One detail, noticed by a trained human eye, that changed the timeline of lunar volcanic history. One geological observation made by a person looking at stone from 100 miles up that revised the model. The history of lunar science is built from such moments. A human observer noticing something specific, something contextual, something that the orbital datasets pointed toward, but could not confirm without the in-person verification that only presence provides. Apollo 17 gave us Harrison Schmitt's orange soil. Apollo 8 gave us Earthrise. Chang'e 6 gave us the first far-side samples. And Artemis 2, Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen, in a spacecraft named Integrity, gave us something that is harder to quantify, but no less essential. The return of human eyes to the vicinity of the moon. The restoration of the human observer to the loop of lunar inquiry. The reconnection of human perception to the ancient surface that has waited there, patient and two-faced, for 4 billion years. The geologic observations made during Artemis 2 will help scientists plan for future missions and answer key questions about the origin of the moon, thus marking another milestone in lunar science and exploration. That is the formal statement. The informal truth is something larger and less containable. The Artemis 2 mission did not close any chapters. It opened them. It placed human observers in proximity to the oldest unsolved problem in inner solar system science and let them look, and what they reported. The colors, the shadows, the textures, the 6 flashes of meteoroid impact on the darkened surface, the corona glowing around the eclipsed sun, the far-side highlands stretching away toward horizons that no human eye had ever seen from this altitude. All of that is now part of the record that the next generation of scientists and explorers will read. I know that the data we will get back will inspire the next generation of scientists and explorers, Kelsey Young said. That is not merely the hopeful statement of a mission scientist at a press conference. It is the description of how science actually works across generational time. One mission building the foundation for the next, one generation's observations becoming the next generation's questions. The picture never complete, but always becoming more complete. Approaching an understanding that is asymptotic in its patience and relentless in its motion. The moon that the Artemis 2 crew saw through the windows of Integrity is not a different moon than the one you see when you look up on a clear night. The geology has not changed. The orbital mechanics have not changed. The tidal lock that has pointed the same face earthward for 4.5 billion years continues to hold, and will hold, long after every institution that built the space launch system has dissolved into whatever comes next in human history. The moon does not need to be understood to be what it is. It was ancient before the first human being looked at it. It will be ancient after the last one does. But the moon you see tonight, if you are someone who has traveled this far with this story, is not quite the same moon you saw this morning. Not because of what you have been told, but because of what you now carry. The knowledge that the familiar face above you is the product of an asymmetry so deep it runs through the entire crust of that world, through its chemistry and thermal history, and the specific violence of its first 100 million years. The knowledge that the face you cannot see, the pale, ancient, battered, creep-poor hemisphere that preserves the record of the near side buried, was looked at on April 6, 2026, by 4 human beings who had spent 3 years preparing for the privilege. The knowledge that what they saw is being studied right now by scientists who are asking more precise versions of a question that has been building since 1959, and that the answer to that question will tell us something about the beginning of everything we stand on. The moon is a mask, as this story began. But it is also more than a mask. A mask covers a face you already know. This one covers a record we are still learning to read. On one side, the familiar, volcanic, creep-rich hemisphere that has watched over every night in human history, shaped by the same ancient fire that also made Earth habitable. Its dark Maria, the legacy of 4 billion years of radioactive heat, driving magma upward through thin crust. On the other side, the ancient, pale, battered, unmodified face that preserved what the near side revised away. The primordial crust, the original chemistry, the deep geological memory of a moon that was new. Between those two faces, the most fundamental question in lunar science still waits for its final answer. The models compete, the samples accumulate. The next mission is being planned. And somewhere in that ancient stone, patient as only 4 billion-year-old rock can be, the record continues to exist. Fully present, fully preserved, available to anyone who comes close enough to read it. The Artemis II crew came close enough. What they brought back is still being read. The moon in front of you is not a sphere. It is a mask, as this story began. One side turned earthward for 4.5 billion years, patient and faithful, and utterly indifferent to the attention we have paid it. You have seen it all your life. Your grandparents saw it. Every human being who has ever lived saw the same arrangement of dark plains and pale highlands, the same Maria pooled in the same ancient impact basins, the same face looking back across the same distance. That face has anchored more mythology, more navigation, more poetry, and more scientific inquiry than any other object in the visible universe. And it is only half of what is there. We have traveled across this long story from the fundamentals of why the moon shows us one face, the tidal breaking, the gradual deceleration over hundreds of millions of years, the synchronous rotation that froze one hemisphere earthward and one hemisphere away, to the moment on October 7th, 1959, when a Soviet spacecraft called Lunar 3 swung around the far side and transmitted the first photographs of a world that had never been seen. Those photographs revealed a surface so different from the near side that scientists immediately recognized the difference required an explanation. More craters, fewer dark plains, a pale, ancient, battered landscape that bore no resemblance to the familiar face. The near side and the far side of the same body looked as though they had experienced entirely different histories. They had. The NASA Grail mission, led by Maria Zuber of MIT in 2011 and 2012, measured the moon's gravity field with sufficient precision to map the thickness of its crust across every point of its surface. The result was a number that crystallized 60 years of observation into a single architectural fact. The far side's crust is approximately 20 kilometers thicker on average than the near side's, 30 to 40 kilometers under the volcanic plains and impact basins of the near side, 50 to 60 kilometers under the ancient highlands of the far side. A structural difference so fundamental that it changed how magma moved, how heat escaped, and how the geological history of the two hemispheres unfolded across billions of years. And the creep terrain, those concentrated deposits of potassium, rare earth elements, and phosphorus on the near side, the radioactive heat-producing elements that powered billions of years of near-side volcanism, is essentially absent from the far side. The heat that kept the near side's mantle partially molten for so long, that sent wave after wave of basaltic lava flooding into the great impact basins and creating the dark maria that have defined the face we know. That heat had a chemical source that one hemisphere had and the other did not. Why? 3 major theories exist, and none has been definitively proven. The thermal gradient of the early Earth, whose surface blazed at perhaps 2,500 degrees Celsius when the moon was young and close and still locking into synchronous rotation, may have preferentially deposited crust-forming minerals on the cooler far side, creating the thickness difference at the very beginning of lunar history. A companion moon, proposed by researchers Yutzi and Asfaug, may have gently merged with the far side in the first tens of millions of years after the moon's formation, plastering additional crust onto one hemisphere. Or a giant impactor, a body approximately 780 kilometers across, modeled by Menghua Zhu at the Space Science Institute of Macau University of Science and Technology in research published in 2019, may have struck the near side with enough energy to redistribute creep material from the deep interior, fundamentally reshaping the near side's chemical identity and burying the far side's primordial crust under kilometers of redistributed debris. Or the South Pole-Aitken basin, which excavated so deeply into the far side crust that it may have exposed mantle material, generated a heat plume that carried creep to the near side, the hypothesis proposed by researchers at Brown University in Science Advances in 2022, connecting the far side's deepest wound to the near side's greatest geological richness. Some researchers favor one explanation, others favor another. The honest answer, as of this telling, is that the origin of the lunar dichotomy remains genuinely uncertain. Not for lack of investigation and not for lack of data, but because the question reaches so deep into the moon's formation history, into the chaotic first 100 million years of the solar system, that the physical record available to us has not yet been sufficient to close the argument with certainty. Into that uncertainty, China's Chang'e 6 mission landed in June 2024 at Apollo Basin, within the South Pole-Aitken Basin on the lunar far side, and returned the first physical samples ever collected from that hemisphere. Chunlai Li and colleagues at the Chinese Academy of Sciences analyzed 1,935.3 grams of far-side basalt and found exactly what the orbital remote sensing data had suggested: a surface depleted in creep, nearly empty of the heat-producing radioactive elements that shaped the near side. Water content between 1 and 1.5 micrograms per gram, extraordinarily dry. Basalts dated to 2.83 billion years old, produced not by creep heat, but by the locally thin crust that the Apollo Basin's ancient impact had left behind. Different in texture, different in composition, different in physical behavior from everything collected from the near side in more than 50 years of prior missions. The first physical contact with the geological archive that the far side had been keeping since the moon was young. And then, on April 1st, 2026, the Space Launch System rose from Launch Complex 39B at Kennedy Space Center in Florida with 8.8 million pounds of thrust, carrying Orion, the spacecraft named Integrity by its crew, and 4 human beings into a sky turning rose and gold over the Atlantic. Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen. The first crewed mission to travel beyond low Earth orbit since Apollo 17 in December 1972. The first Canadian ever to travel to deep space. The first black astronaut to travel beyond low Earth orbit. 10 days, 694,000 481 miles around the Moon and back. They crossed the translunar coast over 3 quiet days, watching Earth shrink and the Moon grow. They entered the lunar sphere of influence at 12:37 a.m. on April 6th, at the moment when the Moon's gravity became stronger than Earth's. Christina Koch described it precisely. They were no longer rising away from Earth. They were falling toward the Moon. For 7 hours on April 6th, they observed. They documented impact craters, ancient lava flows, and surface fractures that will help scientists study the Moon's geologic evolution. They monitored color, brightness, and texture differences across the terrain, observed an Earthset and Earthrise, and captured solar eclipse views of the Sun's corona. They photographed Vavilov crater on the rim of the ancient Hertzsprung Basin. They documented the Terminator Zone, that boundary between lunar day and lunar night, where low-angled sunlight makes every geological feature cast a shadow reaching toward the horizon. In conditions that mirror what Artemis 3 astronauts will face at the lunar South Pole in 2028, they watched Earth set below the far side horizon at 6:41 p.m. and entered 40 minutes of complete silence as the Moon's mass intervened between their spacecraft and every antenna on Earth. They reached closest approach at 4,067 miles above the surface, broke the distance record set by Apollo 13 in 1970, watched Earth rise again above the far side horizon as communications were restored. They saw the Sun disappear behind the Moon for nearly 54 minutes of totality and watched the corona glow in a halo around the darkened lunar disk. And during the darkness of the eclipse, they watched the ancient surface below them 6 times, briefly, brilliantly, as meteoroids struck the Moon and converted their kinetic energy into light. For 67 years, we have been asking why the Moon's 2 faces are different. For 67 years, the answer has been approaching, piece by piece, mission by mission. For 67 years, the Moon has been patient. The answer has not arrived in full. It may not arrive for another decade or another generation, depending on what Artemis 3 finds at the South Pole, on what future sample return missions bring back from specific far-side geological units, on what the intersection of the Chang'e 6 geochemical data and the Artemis 2 observational data and the competing theoretical models eventually produces in the way of consensus. Science does not work on human timescales. It works on the timescale of evidence, which is slower and more reliable. But here is what has been established and what no subsequent discovery will undo. The Moon was made from the same catastrophe that made Earth. 4.5 billion years ago, a Mars-sized body struck the young Earth with enough energy to partially vaporize both objects. And from the debris of that collision, from the mixed material of 2 worlds briefly rendered liquid and then slowly reassembled by gravity, the Moon condensed, not gently, not gradually, in geological terms, almost instantly. A world assembled itself from violence, inherited the chemistry of its parent bodies, and then began, over the next few 100 million years, to sort itself into the 2-faced body we now observe. The near side, facing a hot young Earth, cooled more slowly, accumulated the heat-producing elements, and supported billions of years of volcanic activity. The far side, facing the void, cooled faster, preserved the primordial chemistry, became the ancient and unmodified geological record that no part of Earth itself has managed to preserve. The Earth that you stand on, breathe on, were born on. It has forgotten its own beginning. The geological processes that made it habitable have, in doing so, erased the memory of what it was before those processes began. Plate tectonics recycled the early crust. Volcanism overprinted the original chemistry. Life transformed the atmosphere, The Earth you inhabit is a palimpsest, a surface written on, erased, written on again so many times that the original text is unretrievable. The Moon has not done this. The Moon, geologically quiet for most of its history, has preserved the original text. The far side highlands, that pale anorthosite crust, thick and ancient and creep-depleted and older than anything on Earth, are the nearest thing that exists to the original geological identity of the material that both Earth and Moon were made from. When Chunlai Li's team analyzed those 1,935.3 grams of far-side basalt, they were, in the most literal sense, touching material that preserves conditions from before complex life existed anywhere. When the Artemis II crew looked down at the ancient highlands from 4,067 miles above, they were looking at a record that Earth has permanently lost. The Moon remembers what Earth cannot. This is not a metaphor. It is a geological fact with philosophical weight. We are, all of us, the products of the process that made both worlds. The carbon in every living thing on Earth, the water in every ocean, the silicon in every piece of technology. It all traces back, ultimately, to the cloud of material from which the Sun and its planets formed, which was itself the debris of previous stellar generations. The Moon was made from the same cloud, concentrated through the same violence, sorted by the same gravity. What the Moon's geological record preserves is not alien to us. It is the record of our own origin, kept on our behalf by a world that orbits us faithfully, that has shown us one face for as long as life has existed, that has been our companion through every evolutionary development from the first cell to the first spacecraft. We finally sent people around its hidden face. They were named Wiseman, Glover, Koch, Hansen. They flew in a spacecraft they had named Integrity. They looked at the ancient stone. They reported its colors and its shadows and the texture of its surface under oblique sunlight. They watched it being struck 6 times by ancient debris, while an eclipsed sun glowed above them. They were the first people in more than 50 years to look at the Moon from close range, and the first people in all of human history to look at certain specific regions of the far side with human eyes. And then they came home. The light coming to you from the Moon tonight, if you step outside, if the sky is clear enough, if it is not hidden behind clouds or city glow, is the same light that has reached human eyes for as long as eyes have existed to receive it. Reflected sunlight, bouncing off a surface 4.5 billion years old, crossing 384,000 kilometers in just over a second, arriving at your retina as the cool silver gray that you have known since childhood. Nothing about that light is different tonight than it was last night, or last year, or 1,000 years ago. But you are different. You know now that the face you see is the younger face, the volcanic face, the creep-rich face, the face that Earth's early heat helped shape, the face that has been renewed and resurfaced and modified over billions of years until it reached the arrangement of dark and pale that has anchored human mythology across every civilization. You know that behind it, perpetually turned away, perpetually silent, lies the older face, the primordial face, the face of ancient highlands and absence of Maria, the face of 4-billion-year-old anorthosite that has not been significantly altered since the Moon's magma ocean first solidified. You know that the difference between those two faces is one of the oldest unanswered questions in planetary science, and that the question matters because it is, in the end, a question about where we came from and what the early solar system looked like before everything changed. You know that 4 human beings flew past that hidden face on April 6, 2026, and that what they saw is being studied right now added to the accumulating archive of lunar knowledge that will eventually, not yet, but eventually, produce a definitive answer. The moon in front of you is not a sphere. It is a mask, but it is also more than a mask. A mask covers something and reveals nothing. This world covers its older face while revealing its younger one, and what it reveals is beautiful and volcanic, and shaped by forces we are still working to understand. What it conceals is ancient and pale and preserved, waiting with 4 billion years of patience for the next mission that comes close enough to read it properly. Apollo 8 gave humanity Earthrise in 1968. The vision of our own world rising above the lunar horizon, small and blue and singular and fragile, an image that changed how a generation thought about what they were living on. Artemis 2 gave us Earthset. Earth dropping below the far side horizon at 6:41 p.m. on April 6, 2026, into the ancient battered terrain of the hemisphere that time forgot. Apollo 8 showed us where we came from. Artemis 2 showed us what was there when it all began. And Christina Koch, emerging from 40 minutes of silence on the far side of the moon, with Earth rising again above the far horizon and mission control reacquiring the signal, said the thing that needed to be said, the thing that any of us would have said. It is so great to hear from Earth again. The moon has waited 4.5 billion years. We have been asking the right question for 67. The answer is coming. One mission at a time, one sample at a time, one human observation at a time. And the moon, patient, two-faced, ancient beyond all reckoning, will wait as long as it takes. If this changed how you think about the moon, about that faithful, two-faced companion that has watched over every night in human history, that carries in its hidden face the record of a beginning that Earth itself destroyed, then the time was well spent. Thank you for staying.